In this video, we'll be covering the concept of a frame buffer. It's a very useful data structure that's used very commonly in graphics, and we'll introduce it through a Python notebook. A frame buffer is a region of memory that stores information about the image that's going to be rendered. You'll be interacting with a frame buffer as well as a sample buffer in Project 1 and implementing some functions on top of it, such as supersampling. A frame buffer is an important data structure because it's ultimately the final product of that rendering pipeline. It stores the color values for each pixel that's going to be displayed to the user at some resolution. The frame buffer is just a region of memory. So it's not actually a multidimensional data structure, even though images can often be thought of best as multidimensional arrays. The frame buffer is a linear region of memory where each channel of a pixel, red, green, blue, is stored contiguously, adjacent in memory. And then at a higher level, each row is stored contiguously. So in one region of the frame buffer, red, green, blue of the leftmost pixel will be stored, then red, green, blue of the next pixel. Different rows will be offset. Also, you'll see in Project 1 an intermediate data structure called a sample buffer that can store colors in its different format. The sample buffer can even contain multiple colors per pixel that will be rendered to the user. And that will be useful for supersampling, where you'll populate the sample buffer with multiple samples per pixel and then downsample it to get the frame buffer. Okay, to introduce the code, this is a data structure called a color class, storing the red, green, and blue values of a pixel or a sample. And we'll start by implementing a method to convert an image, which is a three-dimensional data structure, into a sample buffer. And the sample buffer here is also a linear data structure. So we'll start by iterating over the rows for y in range h. H is the height of the image. For x in range w over the columns, we'll want to construct one of these color classes, color objects, to contain the contents of the sample. We'll extract the red, green, and blue values off of the image at position y and x, and then copy it into the sample buffer. So for now, let's just put a placeholder in here for the location. We'll need to compute that. Equals color, red, green, blue. So where do we get the location to populate a sample buffer? This can be computed from the indices y and x. Y gives us the row. And as we move down an image to another row, in memory, we'll be moving over w positions because each row takes w pixels. And then the columns are given by x, which are contiguous in memory. Okay? Now we'll implement a second method, image to frame buffer. This method takes in that sample buffer that we've just produced and copies it into a frame buffer data structure. So the sample buffer, these colors, for example, they might be continuous values from 0 to 1, but the frame buffer stores integers from 0 to 255. And it also stores in a slightly different format. It's a 1D array of, instead of color objects, it's a 1D array of ints. But the code will look pretty similar. So we can go ahead and iterate over the sample buffer in a similar fashion. Range W for y in range h. Let's get the color object off of the sample buffer. Y times W plus X, our column offset. Now we need to copy the three channels and convert them to integers. So for K in range 3, iterating over red, green, blue, we want to copy a value into our frame buffer. Again, at some location, let's just put a placeholder for now. Convert to an int the value of the color. So color, the val, K. index the kth channel of the color. In order to convert this 0 to 1 scaled color to an integer, we'll multiply it by 255, so it's still floating point, but then cast it to an int. And in C++, that might be just represented as a single byte. Okay, so now let's figure out the position in the frame buffer for row X, column Y, and channel K. So let's start with a channel. Channels are ultimately stored contiguously, so they're the last offset we'll add. Incrementing the channel by 1 only increments the memory position by 1. Now, we'll see the same trick from above for the rows and the columns. So moving along a column will move us in memory by 3 positions because there are 3 channels. Moving a row by incrementing y will move us 3 times w positions in memory. Cool. Okay, we've implemented both of these methods. We can test it out on a simple image. And here we go. Not a lot to look at because this is a pure Python example. We're not loading any external data. We could load an external image and render it to the frame buffer, but we'll just create an artificial image of height 200 and width 200. I'll start off with zeros, which means black color, and then populate the left half of the image with red value 1, green, blue 0. So that'll be red content. Convert it to the sample buffer, which is that linear array of color objects. Initialize a frame buffer, which is a linear array of type integer, size height times width times 3. And then convert our sample buffer to the frame buffer. Finally, render it out to screen. And that's where we got this result. Thanks.